Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture number 34 of the course Stochastic Hydrology. We have been now discussing multivariate stochastic models, essentially to generate data on several sites simultaneously, and specifically we deal with stream flow generation, but these can be also applied to other variables, other random variables, provided the data fits the particular assumptions that we make in these models. So, in the last lecture we looked at generation at two sites simultaneously. By simultaneously I mean we also look at the dependence of the flows at one site on the flows at other site. Distinguish this between with what we had done earlier for single site models. In the single site model in the single site data generation models, we considered the time series at a particular site and considered the serial correlations which are also called as the autocorrelations. In the two site model that we discussed in the previous lecture, what we essentially do is we identify one as the key site depending on the length of the data as well as on the quality of the data at that particular location, and the other one we treat it as a subordinate site to the key site that we have identified. On the key site we generate the data using the single site models, and then on the subordinate site we generate the data based on the covariance that exists between the key site, the data at the key site and the data at the subordinate site. So, this is what we essentially did in the previous lecture, where we talked about data generation simultaneously at two locations. So, just to recall the expressions that we developed last time, first we introduced the concept of cross correlation at lag k. So, RJH is the cross correlation between the data at site j and that at site h with a lag k, and this lag k is time lag, and this is how we determine this. So, this is at the ith time period and this is at I plus kth time period, where k is the time lag, and this data refers to the site h data and this refers to site j data. So, this is how we get the cross correlation between data at two different locations and at two different times. So, there is a time lag of k units, k time units between the two data that we are considering. So, I and I plus k, and we also did an example where we considered the lag 1 and then found how to found the cross correlation between two sites. Then we introduced the two site Markov model. This is for the subordinate site, where we are talking about generation at site h. In these models do not worry too much about this capitals and small letters. Actually, this should be a small letter, small x h t, but like I did in regression, most of these the capitals and small letters may mean the same thing, unless we are talking about the matrix notation, which we will do subsequently. So, we are generating the data at the site h for the time period t. We are using the data at site j during time period t. So, this is data at site j during time period t, and we are looking at the cross correlation between the data at site j and site h at lag 0. So, this is just the cross correlation between site j and site h at lag 0, and the term ut here is the random term. and we have seen the expressions for these, and this is again the cross correlation between the site j and site h at lag 0. So, this is how we generate the data on the subordinate site, which incorporates the correlation between the sites, the data at site j and site h. Let us see how we can generalize this now to many sites. Now, from the 2 sites we go on to many sites. When we are talking about a general multi-site Markov model, the aim is to generate simultaneously at all locations. In the 2 site model, what we did was, in the 2 site model that I discussed in this particular course, what we did was that we identified a key site and then generated the data on the key site using single site model, and on the subordinate site using the correlations between these 2 sites as well as autocorrelations. The term UT contains the autocorrelations there. However, when we are interested in developing generation models for for data generation simultaneously at several locations, remember in the watershed you may have 3-4 streams, and your interest is to generate data on all these 3 or 4 streams simultaneously, taking into account their interdependence in as much as there is a correlation that exists among all these data. When we are doing this, we do not go with the identification of key site and so on. We are interested in generating the data simultaneously at all the locations. So, there is no site that distinguishes itself with other sites. All sites are equal in importance, and we are considering the cross correlations among these data at various sites. What we do is, first we work with standardized data. Let us say this is the data now at the jth site for the time period t. We remove the mean from this, deduct the mean from this, and then divide by the standard deviation of the data at the site j, and then form the standardized data. So, we will be dealing with only the standardized data x j t. Now, with this now we will start developing the multi-site Markov models. Remember, we started with the single site Markov model. What we now first do is that we will apply the single site Markov model at all these locations. There are p locations, p stations. Just so that you do not lose sight of the problem, we will just see what we are doing. There are several locations like this, 1, 2, 3 etcetera, p locations. Now, all of these may be stream gauges. For example, this may be a stream gauge, and this may be a stream gauge, and this may be a stream gauge, and so on. So, we have the flow data at this location, we have the flow data at this location, etcetera. So, there are p locations at which you have the stream data, and this may be a watershed, and then you are interested in generating the data at all these locations simultaneously. That is the problem that we are addressing. First, we take individual sites h, j, etcetera. We take individual sites, and then we write the single site Markov model. Look at this single site Markov model. This is what we had developed earlier. This is a stationary model in which the mean remains the same, standard deviation and lag 1 correlations, they do not change from time period to time period. So, this is a stationary Markov model. So, this is a single site Markov model. In this, because we have standardized the data, we can write this as rho h 1, we are talking about the site h for time period t plus 1, this is the generation model. So, for time period t plus 1, this is a lag 1 autocorrelation at site h, and we are using the data for the previous period x h t. Because we have standardized, mu is 0 and standard deviation is 1, plus because of this now I will write, instead of u t plus 1, I will write E h epsilon h t plus 1, and this is 1 minus rho h square at lag 1. So, the rho 1 I am writing it as rho h 1 indicating that it is the lag 1 autocorrelation at site H. So, this is what we do at site H. Similarly, for any site j, we will write the same expression for site j. So, like this for sites 1, 2, 3 etcetera up to p, you can write these models. Now, these are single site Markov models applied to individual sites like this. When we combine these and then want to write a single model for simultaneous data generation, the terms here, different terms that we are introducing, for example, epsilon j t plus 1 that we are introducing, epsilon h t plus 1 etcetera. When we combine these terms must in some sense incorporate the dependence of the flows at site H on flows at site J for all H and J. So, that is what is the exercise that we will do now. So, we write these expressions in matrix form and then try to incorporate and then in fact incorporate the dependence of the flows at one location on the flows at other location through their covariances and perhaps correlations at different lags. In fact, we will consider lag 1. So, we write this expression in a matrix form. We are generating x t plus 1 for p sites. So, x t plus 1 is a p by 1 vector of standardized values now. And then we write this as E into x t, this is not expected value, E is a matrix, E into x t we are using from time period for time period t plus 1, we are using the data at time period t plus g epsilon, epsilon all these are matrices. Now, x t is a p by 1 vector, this has standardized values of the variables at time t. Which means let us understand all these matrices correctly. So, we are writing this as x t now, x t is what we are considering at time period t and at each of the sites. So, this is x 1, x 2, x 3 etcetera x p. Now, these are the data at these various locations. Now, this is the thing, this may be x 1, this may be x 2 etcetera x p, this is x p. And at each location you have n time period data. So, you have x 1 at time period t, x 1 at time period 1, x 1 at time period 2 etcetera. So, we are reckoning this at time period t, that is what forms x t. Then we look at other matrix. E is a p by p diagonal matrix whose jth diagonal element is rho j 1. This is autocorrelation at the jth site at lag 1. So, let us write the E matrix now. So, the E matrix can be written as, we have sites 1, 2, 3 etcetera up to p, and therefore, you will have those many autocorrelations, you will have p by p matrix 1, 2, 3 etcetera up to p, and it is a diagonal matrix where only the diagonal elements are non-zeros. So, I will write this as rho 1 and this is rho 2 etcetera rho p, and all of these are at lag 1. This is rho 2 at lag 1, rho p at lag 1 and so on, and all other elements are zeros here. So, that is why it is called as a diagonal matrix. So, we form the E matrix by putting along the diagonals the first the lag 1 autocorrelations, this is 1 to 1, 2 to 2 and so on. So, this is how we get the p by p matrix. All right. Now, we will formulate the other matrix now. So, E is a p by p diagonal matrix whose jth diagonal element is row j 1. That means, second diagonal is row 2 1, that is at site 2 the lag 1 correlation that exists, that is what we put it as row 2 1. Then epsilon is a p by 1 vector of the random variates. Let us look at the matrix G first. Now, G is a p by p diagonal matrix whose jth diagonal element is root of 1 minus rho j square. Look at these, these are the terms that we are trying to reproduce here. This is root of 1 minus rho h square 1. So, that is what we will reproduce through the matrix G. So, how does G look now? G will appear like this. I will write G as much similar to what we wrote for the matrix E. I will write G as root of 1 minus rho h square 1, that is 1 indicates the lag, then root of, you just look at the expression here, that is p by p diagonal matrix whose jth diagonal element is root of 1 minus rho j square 1. This indicates the site j, and this indicates that it is a lag 1 autocorrelation that we are talking about. So, we will write this as 1 and 1 minus rho 2 square and so on, root of 1 minus rho p square, all other elements are zeros. So, this is the diagonal matrix of size p by p. Interpret the terms correctly here. All these are lag 1 correlations, rho 1, rho 2, rho 3, rho p etcetera, they are all lag 1 correlations. Rho 1 here indicates the lag 1 correlation at site 1, and rho 2 here indicates the lag 1 correlation at site 2, and so on. This is rho p. So, this is how you formulate the matrix G. So, we got the matrix X, which is standardized values, and we have got the matrix E, which is a p by p diagonal matrix with the lag 1 correlations at that particular site, and G is a p by p diagonal matrix much the same similar to E, matrix E, except that the diagonal elements are now root of 1 minus rho j h square. Here it was only rho j h, rho j of 1, and epsilon is a p by 1 vector of random variates. So, epsilon we will write it as, let us say I write epsilon, this is simply epsilon 1, epsilon 2 etcetera, epsilon p, these are random variates. So, this is p by 1. So, this is how we write in terms of the matrix notation the multi-site model. X t plus 1 is equal to E x t plus G into E. What are all known here? You look at all these matrices. X t is the standardized, is a vector of standardized data. This is known because you have at p sites for the time period t, you have the observed data. From the observed data you have standardized, therefore, x t is known. Come to the matrix E. This is at site 1, we are talking about the lag 1 correlation at site 1, that is rho 1 1. This can be estimated, there is a time series available at site 1, therefore, rho 1 can be estimated at site 1. Similarly, rho 2 can be estimated at site 1, site 2 and so on. So, all of these diagonal elements are estimated, and therefore, the matrix E is known. Then we will come to matrix G, again rho 1, rho 2 etcetera are estimated, therefore, matrix G is known. The epsilon, which is the standard variates, random variates, I am not sorry, it is not standard variates, they are random variates. Now, they consist of E epsilon 1, epsilon 2 etcetera up to epsilon p. So, if you look at this expression now, E is known, x t is known, g is known, epsilon is what we have to define. So, that your x t plus 1 gets generated. So, how do we define this epsilon? So, that we are also looking at the cross correlations between different locations. So, epsilon we need to define such that the dependence of data at a particular location on the data at some other location is captured by this model. That is what we will do now. Now, epsilon is defined, the whole crux of this model now depends on how we define the epsilon. We define epsilon such that we are able to preserve the first order serial correlation, which is the autocorrelation. We are talking about rho 1, rho 2 etcetera, all of them are at lag 1. It has to preserve the first order serial correlation, and it should also preserve the lag 0 cross correlation between x j and x h. So, one, the time dependence of the data at a particular site, which is given by the lag 1 autocorrelation. Then the space dependence based on the data dependency on other sites, that is reflected through cross correlations. So, you need to preserve the lag 1 autocorrelation as well as lag 0 cross correlation. That is how we define epsilon now. Now, we make the epsilon independent of x j t. That means, we have the original standardized data values. The epsilons that we are defining are independent of the x t's, that is the one condition. The second condition is we will use normal distribution. So, epsilon is also n 0 1, which means it has a 0 mean and standard deviation of 1. We define this rho j h star at 0 by this expression. Now, this is there are derivations etcetera available. We will simply directly go to the application, so that we will be able to use these models in our applications. I will not go into the derivations of how we arrive at this. So, rho j h 0, that is, this is the cross correlation between site j and site h at lag 0, at time lag 0 is defined by this expression. You look at what we have here. This is rho j at lag 1, the autocorrelation at site j at lag 1, autocorrelation at site h at lag 1, the cross correlation between site j and site h at lag 0, and similarly these are defined terms. We are defining another term here called rho j h star at 0, which depends on rho j h 0. So, this is the term that we define, and we use this term to determine our epsilon. If we define rho j h star 0 in this fashion, it reproduces, when we use this in our model as we will do presently, it reproduces the rho j h 0, which is the cross correlation between sites j and h at lag 0. And also the model that we have used, we have just introduced, it also reproduces the lag 1 autocorrelations. So, lag 0 cross correlations as well as lag 1 autocorrelations is what is preserved by this model. So, we define from this epsilon is equal to a d lambda to the power half e. It may appear too mathematical and without any logic here. What we are doing now is that we are obtaining the expressions for epsilon. What is the objective of this? We want to define epsilon such that it preserves the cross correlation among different sites, and it preserves the autocorrelations at a particular given site. So, that when we write the model in the form that we did, and incorporate epsilon in this particular form, we are able to preserve the mean at all the locations, the standard deviations at all the locations, the lag 1 correlations at all the locations, and the lag 0 cross correlations. So, this is what is needed for our model. So, we define epsilon as a d lambda to the power half into E. We will understand what are all these now. D lambda is a p by p diagonal matrix whose jth diagonal element is the square root of the jth largest eigen value of the p by p correlation matrix, whose elements are rho j h star 0. Understand this correctly. This is what is necessary for our application. First, you look at this correlation matrix defined by rho j h star 0. So, rho j h star 0 is what we have determined here. Between site j and h, you have rho j h star 0 defined. On this now, you form a diagonal matrix. So, this is p by p correlation matrix you have got by j h star. So, this is the p by p matrix. So, let us write that, and then we write the matrix D. So, for this p by p correlation matrix, which is a square matrix, you get the eigen values. We have seen how to get the eigen values for a square matrix. You get the eigen values for this square matrix. Arrange the eigen values in decreasing order, the highest one as lambda 1, next one as lambda 2, etcetera, up to lambda p. It is a p by p matrix, therefore, we have p lambda values, p eigen values. Arrange them in decreasing order. Then you look at the matrix D now. The matrix D will consist of lambda 1, lambda 2, lambda 3, etcetera, along the diagonal, where lambda 1 is the highest eigen value, lambda 2 is the next highest eigen value, and so on up to lambda p. That is how you get D matrix, but we are interested in d to the power half, that is square root. So, you take square root of lambda 1, square root of lambda 2, etcetera. So, that is how you form the D matrix. Let me write for clarity what is the D matrix now. So, we write the D matrix as a diagonal matrix of size p by p. I say it is a diagonal matrix because except the diagonal elements, all other elements are zeros. We write this as lambda 1 to the power half, lambda 2 to the power half, and so on up to lambda p to the power half, and all other elements are 0. And this is what I denote it as d lambda to the power half. All other elements are 0 here. What are these lambda 1, lambda 2, etcetera? I define lambda j as the jth largest eigen value of the p by p correlation matrix. So, this is how you form the d lambda to the power half matrix. I repeat again, you look at this, we are saying it is a p by p diagonal matrix whose jth diagonal element is the square root of the jth largest eigen value of the p by p correlation matrix whose elements are rho j h star 0. So, first look at p by p correlation matrix, which is rho j h 0 with each of its elements as rho j h 0. For clarity, maybe I will write that also. So, the correlation matrix that we are talking about is this, from which D is derived. let us say I have 1, 2, 3 etcetera up to p and 1, 2, 3 etcetera up to p. Now, rho 1 1 rho j h star 0, then rho 2 1 star 0, like this. Any element you take, this will be rho 1 p star 0 and this will be rho p p star 0. That is the correlation matrix whose elements are rho j h star 0. Remember, these are not the original cross correlations. You look at this expression, this is what will define rho j h star 0. So, at a site j with site h, this is the correlation, that cross correlation that you are defining now, and that is the cross correlation that you will use for defining the cross correlation matrix. This is the p by p matrix. You take the eigenvalues, you will get p eigenvalues for this. Arrange the eigenvalues in decreasing order, with the highest one denoting as lambda 1, the lowest as lambda p, and then come to the formulation of D matrix, and D matrix is formed by the square root of D lambda to the power half. That matrix we form it as lambda 1 to the power half, lambda to the power half, etcetera, as a diagonal matrix. Only the diagonal elements are filled, all other remaining elements are zeros. This is how we formulate d lambda to the power half. All these values are known, therefore, d lambda to the power half matrix is completely defined. All right. Then we come to the matrix A. So, this is, we know how to determine d lambda to the power half. Let us look at what is matrix A now. A is a matrix p by p size consisting of eigenvectors of the correlation matrix. So, we had the correlation matrix as we just defined. This is the correlation matrix. And we were determining the eigenvalues. When we determine the eigenvalues, we also determine the eigenvectors of this matrix. The size is p by p, therefore, there are p eigenvectors, and then we formulate the A matrix again as a p by p matrix. This one is eigenvector number 1, eigenvector number 2, etcetera. This is 1, 2, 3, etcetera, up to p. So, this is the p by p matrix. So, A is a matrix consisting of eigenvectors. Because we are talking about eigenvectors of the matrix of size p by p, you have p eigenvectors. So, that is how you define the the matrix A. So, you defined the matrix D to the power half lambda associated with the eigenvalues, and you define now the matrix A based on the eigenvectors of the same matrix. This rho j h star 0 is the matrix that we are talking about. On this matrix, you define the eigenvectors and also define the eigenvalues, and thus you define d to the power half lambda as well as the matrix A. Now, we will come to E. What is this E now? E is a p by 1 vector of independent observations from n 0 1. So, this is essentially the standard normal variate. So, E is p by 1. So, I will write it as maybe we will write it here only. So, E is all right, we will write it on the separate sheet. So, E is, now I define this as E 1, E 2, E 3, etcetera, E p. So, this is the p by 1 matrix. What are all these? These are n 0 1, that is standard normal deviate. So, you can just generate these from the normal distribution. So, we have now defined all of these terms now. The matrix A is defined, matrix D lambda to the power half is defined, and E to E is defined, and therefore, we should get epsilon. Now, A is a p by p matrix and this is a p by p matrix. So, this is p by p into p by p, I get a p by p, and then this is a p by 1 matrix. So, I get p by 1 matrix. So, epsilon is a p by 1 matrix, that is what we have defined here. Epsilon is a p by 1 vector of random variates. What is all the information that has gone into defining epsilon? We have essentially used rho j at star 0, which reproduces the way we have defined rho j h star 0, in fact reproduces the cross correlations among different sites j and h for all j and h. This is the information that we have used in defining epsilon. We use the eigenvectors of that matrix, we use the eigenvalues of that matrix, etc., but essentially we have used the elements rho j h star 0. When we define epsilon by this, it essentially reproduces the dependence of values at one site on the values at several other sites. Remember, you are talking about j, site j, and h can vary, h is equal to 1, h is equal to 2, etc. So, you are reproducing or you are capturing the dependence of the values at site j to values at with values at several other sites, all other sites in fact. Now, this is the general form x t plus 1 is equal to E x t plus g into E. This is a multivariate stochastic model that we use in a most general form for generation, simultaneous generation at several locations, and this is a common general model. However, for specific case of flow generation in several locations in a watershed or in a catchment, a classic model developed by Matelas, it is in fact called as a Matelas model way back in 1969. It is a very rigorous model and it has been validated for several locations, and we generally use for multi-site data generation, we use the Matelas model in hydrology. It follows the same broad structure, except that what we did here is to incorporate our cross correlations among different sites. That information we incorporated through epsilon, and here what we did is the lag 1 correlations, which means the time dependence, we have put through the vector E here or the matrix E here. This structure is slightly different in the Matelas model. Let us look at the Matelas model and how we use the Matelas model for multi-site data generation simultaneously. Following the same general structure of the model that we discussed just now, Matelas has proposed this model, and this is a reference, and this reference is is available in the C.T. Hahn's book. I have taken it from the C.T. Hahn's book. In fact, this area classically it used to be called as synthetic hydrology, and Thomas and Fearing, Matelas, they have made very significant contributions in data generation at several locations. In India, it has to pick up, these techniques have to pick up for water resource planning, management and operations, etc. But these techniques are available, they are very elegant techniques and they can be programmed easily, and therefore, the students of this course must be geared up to apply these kind of stochastic models for actual applications, especially in terms of watershed management, in terms of the reservoir operation and so on. All right. Now, look at this structure now, x t plus 1 is equal to a x t plus beta epsilon t plus 1, or we will call it as B. The coefficient matrix I call it as beta, this capital B also indicates betas. Now, to generate x t plus 1 we are using x t and some random component here epsilon t plus 1. Now, x t being the data, remember we have p sites, at each of the p sites you have the time series t is equal to 1, t is equal to 2 etcetera, there are n time periods. So, x t is known and x t plus 1 is known, and these we standardize, we use the standardized data. By standardization I mean deduct the mean and divide by the standard deviation. These are known. Now, we have to determine the matrix A as well as the matrix epsilon now. So, let us see how we do this. The MATLAS model that we are just going to discuss is a multi-site normal generation model. It preserves the mean, the variance, lag 1 serial correlation and lag 1 cross correlation. In fact, lag 0 cross correlation also. So, it preserves all these parameters, the mean, the variance, lag 1 serial correlation or the lag 1 autocorrelation at each of the sites, and lag 1 cross correlation between different sites. You know how to determine the lag 1 cross correlation, and then the lag 0 cross correlation. All of these parameters are preserved. What do I mean by preserved? When you do the data generation using this model, the generated data will have, in a statistical sense, same values for all of these parameters as the historical observed data. That is what we mean by preserving these parameters. This is a normal distribution model. It is it uses normal distribution. The assumption is that the model is a multivariate normal. What does it mean? At all the p sites, typically we are using it for flows, at all the p sites the flows follow a normal distribution. That is what we mean by model is multivariate normal. Now, these are p by 1 vectors. So, x 1, x 2, x 3, x etcetera, x p, they are all normal, they all follow normal distribution is the assumption. So, this you should not forget, and that is why we use these kind of models for, let us say, monthly stream flow data, seasonal stream flow data, etcetera. We cannot be using this for daily rainfall data, where obviously the assumption of a normal distribution is not valid. So, whenever you are using such multivariate stochastic models, you must keep in mind that these are applicable, especially the ones that I am discussing in this course, are applicable only when individual variables x 1, x 2, x 3 etcetera up to x p, they all follow normal distribution. All right. Now, we will start defining what are these matrices now. Epsilon t plus 1, here this matrix is n 0 1. So, normal distribution, it is a standard normal distribution. It is a p by 1 vector, epsilon 1, epsilon 2 etcetera up to epsilon p at time period t plus 1. A and B are coefficient matrices of size p by p. Look at this, this is p by p, this is p by p, and this is p by 1, and this is p by 1. So, you will get p by 1 here for x t plus 1. So, x t plus 1 is for time period t plus 1, I am writing x 1, x 2, x 3, x I and x p. So, these are the observations at different sites here at time period t plus 1. Similarly, x t is observations at different time different sites at time period t. These are at different sites, there are p sites available, and epsilon t plus 1 I will write as epsilon 1, epsilon 2 etcetera at time period t plus 1. This is p by 1, this is p by 1, this is p by 1. So, in the scalar form if we write, that is this expression now, this expression I am writing in a scalar form. There is a matrix A and matrix B, which are both p by p matrices. So, I will write this as A I j. Look at this, I am writing for the ith site for time period t plus 1. The elements of the matrix A are A I j, the elements of the matrix B are B I j. So, I will write this as j is equal to 1 to p A I j x j t, and j is equal to 1 to I b I j epsilon I t plus 1. I am writing this. Now, there is a reason for going up to I will come to that. We are assuming the matrix B to be a lower triangular matrix, which means all the upper values from the diagonal are all zeros, only the lower values are not zeros. When we do that, we can write it in this fashion, J is equal to 1 to I. I will explain this further when we are developing the notations for matrix B. But this expression arises out of the assumption that the matrix B is a lower triangular matrix. If we do not assume that, then we cannot find unique solution. In fact, there will be infinitely many solutions possible. Remember, this is a kind of regression that we are doing, where you have to estimate the matrices A and B. Look at this expression, A and B is what you have to estimate, because x t is based on the observations and epsilon t is based on your random numbers n 0 1. So, A and B are the ones that will determine these models. So, the exercise now is to define A and B. All right. Now, this is a scalar form, I do not think it is necessary. As we progress, it will be clearer. Essentially, what we are doing is, we are using the elements of matrix A, Aij, elements of matrix B, which is Bij, and we are assuming B to be a lower triangular matrix, in the sense that all the elements to the right and top of the diagonal are all zeros. Okay. Now, the exercise is to determine the coefficient matrices A and B. Let us understand this correctly. Let us say we take the product x t dash. X t is a p by 1 matrix, and this is x t dash will be 1 by p. So, you will get a p by p matrix. We take the expectation of this matrix x t dash is transpose of x t, and we denote it by m naught, m 0. Why m 0? We are taking x t and x t itself, that is the same time period. We can define m 1, which we will in fact define m 1 as x t and x t minus 1 or x t plus 1, when we lag it by one time period. So, because we are considering the same time period, we will denote it as m naught, and m naught is the expected value of x t dash. In this now, can we write this x t and x t dash? Let us write this matrix, so that it is clear. X t is a p by 1 matrix, you have x 1 t, x 2 t etcetera up to x p t, and x t dash is a 1 by p matrix, x 1 t, x 2 t arranged in a row, and then we have to take a expected value. Remember, we are talking about expected value of a matrix. The expected value of a matrix is a matrix of expected values of individual elements. So, this is the one thing that you must remember. So, let us see how we get this x t dash matrix, because that is critical to the discussion that we will have further. Your x t is a p by 1 matrix consisting of the observations at p locations, standardized observations. So, I will write this as x 1 t, or to be more clear, we will write this way x 2 t etcetera x p t. Now, this is p by 1 matrix, and this we call it as x t. This is x t matrix, and x t prime, let us multiply it now directly. So, I will write this as x t, and I will write x t prime. X t prime is simply transpose of this. So, this will be x 1 t, x 2 t etcetera x p t. This is 1 by p matrix. So, you should get a p by p matrix. Now, that p by p matrix will write, at least a few elements will write. so that it will be useful in our further discussion. So, when I multiply this, what happens to the first row? Okay, let us take this, the first row I will define now. This will be x 1 t into x 1 t, x 2 t into x 2 t, x 1 t into x 1 t and x 1 t into x 2 t, x 1 t into x 3 t, etcetera, x 1 t x p t, that will define your first row. So, let us write that x 1 t x 1 t, this is the first element, and then x 1 t into x 2 t, x 1 t x 2 t, etcetera. I come to x 1 t x p t. This is how we get the first row. So, any ith row if I want to write, it will be x I t x 1 t, x I t x 2 t, etcetera, x I t x p t, and last row is x p t x 1 t, x p t x 2 t, and so on, x p t x p t. What is it that I have done now? I have taken x t x t dash, and that multiplication is what I have shown here, and this matrix that we get, which is a p by p matrix, this will be p by p, and this is x t x t dash. Okay. So, this is what we got now. We have to take the expected value of this. So, we are talking about the expected value of x t x t dash, and as I said, expected value of a matrix is a matrix of expected value. So, I will take expected value of this term, expected value of this term, etcetera, and then form the matrix of expected values, which is the expected value of this matrix. That is what we will do now. So, an individual element there, if you look at this point now, at any point you have x I t x j t, I j if you take, or in this case you are looking at an element x I t x j t, and then you are taking the expected value of this. What do I mean by expected value? It is the time average that you are taking at that location I t and j t, and you are taking the time average. So, when I take the time average, I can write the I jth element of the matrix M naught as 1 by n x I t x j t. This is a estimate for the expected value. So, expected value x I t x j t, I will simply take it as time average, and this is x I t x j t, t is equal to 1 to n divided by n, where n is the number of time periods. And that is how we define the matrix M naught, where all the elements are defined now, and M naught is a p by p matrix. Now, look at this now, x I t x j t. What are these? These are the standardized values of our original observations. Let us say you are looking at the flows, and we denote the flows as q. So, what is x I t? It is simply a standardized value of q, namely q minus q bar by s, where s is the standard deviation, q bar is the mean. And therefore, I will write this M naught I j, which is the I jth element in the matrix capital M naught, as 1 by n t is equal to 1 to n q I t minus q I bar. This is the original observed value, and it is a mean, and that is a standard deviation at site I, similarly at site j. And we are calling it as M naught because we are reckoning to the same time period t, t here on both the sides I and j. where q is the original random variable before standardization. For example, it can be stream flow. Can you look at this and identify what is this? This is q I t minus q I bar into q j t minus q j bar. So, this would have been the variance, covariance when you are summing it and dividing it by n, and then you are normalizing with S I and S j, and therefore, it in fact indicates the correlation, cross correlation between the flow at site I and site j. So, m naught is in fact the cross correlation matrix at lag 0. We are not considering any lag here, we are talking about the time period t itself. So, we know how to formulate the matrix m naught. We will progress and see how we formulate a matrix m 1 now, which will consider lag 1 with respect to time. So, essentially what we did today is that we started with the multivariate stochastic model, where we are talking about preserving or taking into account the dependence of flows or dependence of the variable at one particular site on the variable at this at a different site. For example, you are talking about flows in a particular site to the flows in another site, and we gave a general expression for these kind of multivariate stochastic models, and then we have just introduced the classical Matalas model, where we write x t plus 1 as a x t plus b epsilon t, and our purpose is now to estimate a as well as epsilon t. The assumption, underlying assumption in this model, Matalas model, is that it is a multivariate normal model, which means that all the variables have normal distribution, and we are talking about site 1, site 2 etcetera up to site p. You are looking at generation of data at all these sites simultaneously by accounting for their dependence on each other. And so, we have just come up to perhaps halfway of developing the Matalas model. Our final aim is to arrive at these matrices A and B, and also define the matrix the vector epsilon, such that you will get x t plus 1. So, we are writing the expression for x t plus 1, which is the data at time period t plus 1, as dependent on data at time period t at all these locations. And this model preserves the mean, the standard deviation, the lag 1 autocorrelation, the lag 1 cross correlation, as well as lag 0 cross correlation. All of these parameters are preserved by this model, and therefore, it is a powerful model in terms of data generation, for especially for stream flows, especially for monthly stream flows, where your assumption of normal distribution is reasonably valid. So, we will continue this discussion in the next lecture, where we will complete the development of the Matalas model and discuss an example to drive home the point of actual applications. Thank you very much for your attention.